so this is our AP Chemistry lesson video for Chapter 15. This is part 1, and I'm going to cover section 15.1 and 15.2. So, this is the day we start the journey called equilibrium. Alright, so y'all, whether you love it or you hate it, there's 3 chapters of it, and it is a larger portion than most other topics on the AP test. That and intermolecular forces, they're a slight more percentage than some of the other topics. Alright, so you might as well just grin and bear it, because we got to make it through 3 chapters of it. Alright, so let's start with some of the easiest stuff, and we'll work our way up to some of the harder stuff. So, at equilibrium, 2 opposing processes are occurring at the same rate. So that's the whole basis. Is equilibrium, there has to be something equal. So what's equal? The 2 opposite processes. So, for example, vapor pressure of a liquid in a closed container. So if you watch the picture, you'll see that some are evaporating while some are condensing. Once the evaporation rate and the condensation rate are equal, that's when we're at equilibrium. So like if more are evaporating than condensing, you're not at equilibrium. The rates have to be the same. And in a nutshell, that's all equilibrium is. But obviously it gets more complex than that. So let's just keep on going. So in chemical equilibrium, the rate at which the products are formed from reactants equals the rate at which reactants are formed from products. So that's why you'll see like the double arrow in the reaction. As a result, concentrations cease to change, making the reaction appear to have stopped. So what happens is our reactants start decreasing, our products increase because reactants turn into products. Eventually, they will hit what is a steady amount. So it seems as though the reaction has stopped, but what that means is once it reaches equilibrium, every time A converts to B, a B converts back to A at the same rate. So it hasn't actually stopped, it would just appear to have stopped. So equilibrium mixtures occur in reversible reactions. So like I said, you'll see the double-sided arrow. Most of the time what it'll look like is actually this. Okay, it's just easier for me to type the 2 arrows like that. But this is what it normally looks like. So the arrow pointing to the right is considered the forward reaction, and the arrow pointing to the left is considered the reverse reaction. So if you look at our picture, N2O4 is actually colorless. So here we just have N2O4. NO2 is a brown gas. So here you can see it's brown. Well, here I have some of each. We're at equilibrium here. And so you can see it's not colorless, but it's not as dark as this. So that means we have some N2O4 and we have some NO2. So at equilibrium, you're going to have some reactants and some products. So the forward reaction has a rate. And so if this is a elementary step, the forward reaction would be rate equals K. They put a little F to show you that it's for the forward reaction since there's 2 reactions happening here. And then if this is an elementary step, then it's based on the reactants, so N2O4. However, let's say we're focusing on the reverse reaction instead, so we're going from products to reactants. Alright, well, if it's an elementary step, your reverse reaction would be rate equals K reverse. So this is K for the forward reaction. This is K for the reverse reaction. And if this was elementary, then it would be NO2 squared, because it has a 2. Alright, the rates are equal, so these have to be equal if we're at equilibrium. So what that means is K forward times concentration N2O4 equals K reverse times NO2 squared. So once you solve for K instead, you get K forward over K reverse equals NO2 squared over N2O4. And your K over your K is going to be a constant, okay? And that's referred to as our equilibrium constant. Now don't worry if you're like looking at this thinking, what the heck? This is just me proving where the K formula that we're about to talk about comes from, okay? They will not ask you to prove this, okay? I just like to prove it to you. All right, so it doesn't make any difference whether we start with reactants, products, or a mixture of the 2. At equilibrium, the ratio equals a specific value at a certain temperature. So just like the rate K, and this is going to be the difference, the rate K is a lowercase k. Equilibrium K is a capital K. Oh, it changed this to a capital K, probably because it's the first thing I typed. This should also be lowercase. So lowercase rate K depends on temperature. Well, uppercase equilibrium K also depends on temperature. Okay, so here you can see I started with no NO2. I just started with N2O4, and this is where we ended. Here, I started with only NO2. I started with no N2O4. And you can see we end up at the same spot. So it doesn't matter what you start with. Equilibrium is going to happen. At equilibrium, the concentrations of the reactants and products do not change anymore, and the rates of each process are equal. So remember, once you hit equilibrium, you'll see those lines level out. And so again, it doesn't matter what you start with. Okay, notice the front of these look different, but once I hit equilibrium, it's the same for both. All right, and so those rates are the same. So like on a graph, if it said, you know, where did it hit equilibrium, you just need to look at where those lines level off. But like I said, the rates are the same. So you can see here, this is a plot of the rates instead of concentration, and so eventually they are the same once you hit equilibrium. So 3 important equilibrium concepts. At equilibrium, the constants of the reactants and the products no longer change. But the reaction is still occurring. For equilibrium to occur, neither reactants nor products can escape from the system. So it needs to be a closed system. Like if you're producing a gas and the gas is allowed to leave, equilibrium can't be achieved. At equilibrium, a particular ratio of concentration terms equals a constant. And so that's the K value that we're about to talk more about. So what is that K value and how do you get it? So the constant formed by the ratio of the concentration of products to reactants is called the equilibrium constant, which is represented by capital K. I was about to reference what the C means. Capital K. So sometimes you'll see KC, KA, KB, KSP, KP, the subscript KW. The subscript just lets you know what type of K you're talking about. So if you see KC, we are referring to concentrations. All right, so KC, KP, all the Ks are products over reactants. That's the easiest way to think about it. Okay, because a lot of the questions on the AP exam are actually conceptual questions. Even though we'll do a lot of math in my lesson videos, a lot of them are conceptual questions. And so it's always easiest in your mind to think, okay, any K is products over reactants. So if you need to change K or you need to figure out what's going to happen with K, you can always remember that. So it's a little more specific than that though. So you take your products, so here's my D and E, and you raise them to their coefficients as a power. So like D to the D power, E to the E power, over your reactants. So A to the A power, B to the B power. And then like I said, the C in KC means that the values are concentrations. And so in that case, we have a unit of molarity. All right, so for example, if this was our reaction, okay, remember it's products over reactants. So I'll start over here. So it's NH3, but because it has a 2, it's squared. All right, and then over my reactants, so it's N2, which has no coefficient, so I don't need a power, and H2, which is to the 3rd power. Now, unlike the rate law, equilibrium expression can always be written from the balanced equation. So you know how for rate laws, we had to know it's an elementary step, otherwise we couldn't just use the reactants? Well, in equilibrium, it's always based on the balanced equation. The value Kc depends only on temperature. So if they ever talk about, oh, well, if you increase this amount, what happens to K? Well, if you didn't change temperature, nothing happens to K. So the value Kc depends only on temperature, not on the initial amounts of products and reactants. So it doesn't matter what you start with, K is based on temperature. So let's look at the first one together. So it says, write the equilibrium expression for the following reactions. And so I have these 3 right here. All right, so let's look at those together. So of course, K is just products over reactants. So for this one, I'll start, and we would do O2. But because it has a 3 as a coefficient, I'm going to do to the power of 3. And then I do over my reactants, which is O3 to the power of 2, just like that. That's all you have to do for these. So super easy. Again, we're starting out super easy. I don't want to scare you about equilibrium on the very first video. All right, so let's look at this one. So this one, my K value would be products. So I have my NOCl, but because this has a 2, I'm going to square it over reactants. So I have NO, but it has a coefficient of 2, so I'm going to square it. And then Cl2, which has no coefficient, so I'm just going to leave it as is. All right, and then last one is our bottom one. So we have products. So right here, I have my Ag NH3 2 positive over my reactants. So I have the silver ion, Ag positive, and I have my NH3, but I need to square that because it has a power of 2. Just like that. Okay, so the faster you get at writing K values, the better the rest of this will become. All right. Whoop. Oh gosh, sorry, I thought I had my answer wrong down here. Whoop, moving on. All right, so y'all try this one. I'll assume that you've already paused it, tried it, and let's look at it together. So it says write the equilibrium constant Kc for the following reactions. So hopefully you did just like I showed you. So you have products, so in this case Hi, but it's going to be squared over reactants. So we have H2 times I2, just like that. So hopefully you got that right. All right, and then bottom one, same thing, products. So I'm going to grab this ion right here, so CdBr4 negative 2 over my reactants. So I have Cd with positive 2, and I have Br negative, but because it has a coefficient of 4, I'm going to raise it to the 4th power. Oh. So hopefully you got those right. So let's keep on going. Alright, so when using the Kc expression, equilibrium concentrations must be used. Okay, so sometimes they'll tell you what you start with, your initial concentrations. You cannot plug those into a K value. You have to have equilibrium concentrations. Kc and any of the other Ks have no units. And Kc or any of the other Ks do not change as initial concentrations change. Okay, so it doesn't matter what you start with, the thing that changes K is temperature. Alright? So Kc, as we've already discussed, has concentrations in terms of molarity. So like when you're looking to plug into this, you'll want to plug in molarity. However, a lot of times we like to use gases, and we don't use molarity, we use pressure instead. So Kp uses partial pressures in terms of atmospheres, but it doesn't have to be. It could be in torr, it could be in kilopascals, it could be millimeters of mercury. They just all need to be the same. All right, so you set up the formula the same way that you do. Products over reactants raised to the coefficients as powers. However, instead of doing like for this concentration of D to the D power, you'll do P sub D. That implies it's the pressure of D to the power of D. So that's what you would do. So that's the only difference. So sometimes on the AP exam, they'll ask for Kc and you use brackets. Sometimes they'll ask for Kp and you use pressure with the subscripts and the powers with parentheses. Okay, so y'all, if they ask you for Kp and you give them the correct Kc, you get no points. All right, so let's try to make sure that we know what they're asking for. All right, and so then what if you got Kc but you want Kp, or vice versa? There's a formula to convert between the two. All right, so Kp is Kc times R times T raised to delta N. So delta N means change in moles of gaseous product minus moles of gaseous reactant. So notice it's not just moles of products minus moles of reactants. They have to be gases. Okay, so let's look at one together. So it says in the synthesis of ammonia from nitrogen and hydrogen, here's our reaction, Kc is 9.6 at 300 degrees Celsius. Calculate Kp for this reaction at this temperature. Okay, so from the previous slide, we said Kp is Kc times RT raised to the delta N. All right, so first of all, let's figure out what we know. So we know our Kc. We always know R. R, of course, is on our formula sheet. We know T, because we can add 273 to that, and then we can figure out delta N. All right, so let's do our delta N first. All right, so remember, delta N is moles of gaseous product. So if I look, I've got 2 moles of gases on my product side minus moles of gases on the reactant side. So both of these are gases, so I actually have 4 moles. So that's going to give me -2. Okay, so my power right here is going to be -2. For this, I do need to change it to Kelvin, so I add 273, and that ends up being 573 Kelvin. All right, and then it gave me Kc right here. All right, so then I'm ready to plug in. So Kp is Kc, which is 9.6, times my R value, which is 0.0821, liters times atmospheres over moles times Kelvin, times my 573 Kelvin, all that raised to the -2. Okay, and since Kp is going to have no units anyway, you really don't even need to put units in here. All right, and so all I did was just solve this. I multiplied these, raised it to -2, and then multiplied by the 9.6. Important thing is, y'all, only these numbers are raised to the -2. See how there's parentheses? Only R and T are raised to the -2, not the Kc. So you may want to do it like kind of backwards in your calculator. Multiply these, raised to the -2, and then multiply by 9.6. You know, you don't want to miss something over a calculator error. And so I ended up getting 4.3 times 10 to the -3, and K values have no units. Okay, Kc, Kp, later Ka, Kb, Ksp, Kw, none of them have any units. All right, so hopefully that wasn't too bad. It was just plugging into a formula and solving. Hopefully you should not be struggling with equilibrium yet. All right, so y'all try this one. I'll assume that you've already paused it, tried it, and we'll look at it together. So it says for the equilibrium of this reaction, Kc is 4.08 times 10 to the -3 at 1,000 Kelvin. Calculate Kp. All right, so we know that Kp is Kc times RT raised to the delta N. All right, well they gave me Kc. I always know R. I know my temperature, and it's already in Kelvin. So let's get that delta N. Okay, so remember delta N is moles of gaseous product. So I have a gas and I have a gas. Now notice the 2 examples I gave you, they were all gases. But let's just pretend like this was a solid. Then in that case, I would not use that. I'd say 2 moles of gas minus 2 moles of gas. But here, this is a gas. So I have 3 moles of gas on my product side. Minus, on my reactant side, I only have 2 moles of gas. So my delta N is, of course, 1 this time. All right, and so then I just plug in. So Kp is Kc, which is 4.08 times 10 to the -3, times my R, which is 0.0821. I'm just going to leave off units this time, because like I said, they just all go away anyway. Times my temperature, which is 1,000 Kelvin, raised to 1. Look, I said I was leaving off units, and then I immediately wrote them. I like writing units. All right, and so once I solved for all of that, I ended up getting 0.335. And again, no units for K values. All right, so hopefully you got that one right. So let's keep on going. Oh, okay, just kidding. Let's not keep on going. All right, so that's it for video number 1. So hopefully so far you are not struggling that much with equilibrium. Like I said, when the going is tough, just keep on going. Okay, because it's going to be on the AP exam, whether you